Namaste. Welcome back to the next week's lecture in the course of Physics of Nanomaterials. In this week, we will start a very interesting application area of nanomaterials, and that is energy applications. Energy is one of the most talked about and sought after technology in present day scenario. We only talk about renewable energy, but there are various other applications where energy generation, energy storage and energy transmission are equally important. So, in this week we will be talking to you about the use of some novel nanomaterials in the area of energy. We will start with broad perspective, then we will start taking individual examples ranging from generation technologies, storage technologies and transmission technologies. So, in this week we will talk to you about the importance of nanomaterials for energy devices. Primarily, we will talk to you about energy generated from renewable sources. So, we will talk about use of nanomaterials in technologies utilized for energy generation from renewable sources. The need for energy storage and materials which are important for such storage technologies. We will talk to you about secondary batteries as well as supercapacitors. Then we will also talk about energy transmission and energy conversion from one form to the other, so that you can utilize the energy generated from renewable sources for various applications. So, if you talk about need for generation, storage and come back to generation, then you will find that mostly we talk about energy generation. For example, using solar, wind, you can use geothermal and so on so forth. But the first two have become very important for our country. And if you look into these two technologies, they have an intrinsic limitation that they are intermittent in nature. That means, if you look into solar energy, what do you know? You notice that you do not have constant supply throughout the day. If you take the 12-hour cycle, that means you have day and night, then you have periods of 12 hours where it is dark and there is no sunlight. Even if you go back to your 12-hour daytime, then also you do not have the same intensity and the inclination of the source also continuously changes. So, sun rises from east, goes to west via south. So, if you have a solar cell, there is a continuous change in the inclination at which the solar radiation is hitting the generation unit, let us say the PV cells, the photovoltaic cells. Along with that, we know that early morning and 12 noon, you have very different intensities. Hence, you can say that solar energy has an intermittent character, meaning the source is not always available. Source is not always available. Along with that, you see that as weather changes, and if you go into various climatic seasons, for example, from summer to monsoons to winters, there also the duration for which sun is available varies, and if you are talking about monsoon seasons, the skies are cloudy or you have rains, and at that time you do not have sun even during the expected 12-hour daytime. So, what is the way out? This we need to ask. Similarly, if you look into wind, wind is also intermittent in nature. You know that it depends on altitude, location, and the wind speeds are not always constant. So, they are continuously fluctuating. There are very rare times that the wind speeds remain constant throughout the 24-hour cycle. So, what is the way forward? Wind also becomes intermittent. Hence, there is an intrinsic limitation to these two technologies which are becoming important. If you talk about geothermal, sun is hitting the sun, is hitting, let us talk about geothermal. So, sun is heating the ground and then you have that heat can be collected and you can use it for some generation purposes, but that also becomes intermittent in nature. So, as you look into any renewable based energy generation source, you can talk about waves, you can talk about tidal, you name it, and there is a problem of intermittent nature associated with it. So, there is generation, sure, but if you now look into the curves when you require this energy, you will find that you can generate, let us say, during the day, but the requirement during night are much higher for domestic purposes when people return to home after the day's work. So, you need energy, but the source is not available at that time. So, what should you do? That means store the energy when the source is available and you can use technologies to generate energy, use the energy which is required, and the excess energy needs to be stored for a later use. Hence, you need storage technologies, and that is where the renewable based energy landscape has a combination of storage and generation units. So, it is not always that you need materials in energy generation units. Actually, the future would be a combination of both, that is storage and generation unit, that will make a system sustainable and secure. And this is where you will see the massive utilization of nanomaterials both in generation as well as storage technologies. So, let us now start seeing the importance of nanomaterials in energy devices. As I said, we are moving towards a renewable based landscape, which will mitigate the issues of environmental pollution associated with fossil fuel based generation units. You must see that the nanomaterials, if they are being used in such devices, they have to be devices which can give you high efficiency and durability while ensuring reusability. So, these systems must perform processes like light absorption, conduction, or water splitting, catalysis, but they must ensure high efficiency. In addition, if we want to use nanomaterial and replace the bulk materials, what is our wish? Our wish is that along with high efficiency, durability, reusability, I also want to reduce the size of the device, reduce the cost of the device, reduce the weight of the device, and you must have a lower carbon footprint of the device itself. So, you must ensure that if you want to use nanomaterials in such devices, they do not have a very high carbon footprint. Otherwise, they are not a green technology. It seems that they are a green technology, but they would fail in the criteria of having low carbon footprint, which would then take them away from being a green technology. Once we can ensure this, then only we can have a cleaner energy source generation as well as the storage or transmission. So, if you look into the use of nanomaterials, you will find that you can use 1D type materials, 2D type materials, or even 3D type confined materials. You can use them for energy generation. You can use them in thermoelectric devices, piezoelectric devices, triboelectric devices. You can also use them in solar cells and fuel cells, where you can also have energy generation and conversion processes. You can use them for energy storage, let us say electrochemical systems like supercapacitors and batteries. You can also use them in mechanical energy storage systems, electrical energy storage systems, thermal energy storage systems, or chemical energy storage systems. Finally, you can utilize them for energy transmission. You can use them in superconducting coils, flywheels, or you can use them as insulating materials for charge storage. So, you can have utilization of these systems in all the desired parameters associated with the energy landscape, and if we can prove that they have lower carbon footprints also, then they become an ideal replacement for the bulk materials which were and are still being used in many of these applications. So, if you look into energy generation, you have systems like thermoelectric generation. So, what do? This is the way you generate thermoelectricity. Thermo means temperature. So, as the name indicates or suggests, this is a phenomena which utilizes the concept of temperature difference, which creates an electric potential. It is a solid state device that provides direct electricity conversion from thermal energy to electrical energy. What happens here? When the junctions of two different metals are maintained at different temperatures. So, you maintain them at different temperatures and EMF is produced in the circuit. So, you have an EMF generation. This is known as the Seebeck effect. So, if you have a temperature difference between the hot and the cold sides, it causes charge carriers, that is electrons in the n type semiconductors and holes in the p type semiconductors to move and generate electricity and giving you a potential. This voltage drives the current, meaning electricity can be obtained using Seebeck effect. Now, where do you get the application of nanomaterials in this? We have seen that you can have various types of nanomaterials which are semi-conducting in nature. So, you can have different types of nanomaterials. You can change the band gap in such materials. So, as you change the band gap, the energy required for the charge carrier to go from the valence band to conduction band can be tuned, and because of this tunability you can get different mobilities and conductivities of the charge carriers, and hence your capacity to have charge carrier motion, that is dq by dt, that is the current, also will get modified. So, depending upon the temperature difference you can generate, you can tune the band gaps of these materials and choose a material which would allow the excitation from the valence band to the conduction band within the expected temperature ranges which you are expecting in the area where this device is going to be used. And then you can monitor the electricity flowing through it, and then you have a current flow. So, you can make various types of nanomaterials, you can tune the band gaps, you can control the confinement, you can make arrays of such nanoparticles, you can have self assembled nanoparticles, and each will give you a different response characteristic, and hence you can make a large number of devices, or you can make a device as per the requirement of the end user by choosing the right nano material. Very simple strategy. You know how to make nanomaterials, and therefore, you now also know how to make a thermoelectric generator. Similarly, you can have a piezoelectric generation. We know that piezoelectric materials generate an electric charge in response to mechanical stress. Now, if you look into nanomaterials, so you now make nano sized piezoelectric materials. So, piezo ceramics which have high surface area. These systems will be easy to polarize by an applied magnetic field in comparison to bulk, just like what we had studied in the elongated grain concepts while we were talking about the magnetic effect. So, if you draw a PE loop, you will find you can get the systems which will get polarized and give you a hysteresis loop. So, you get a piezo ceramic or a piezo material. So, now when you make small size particles, you can generate polarization at lower fields, and hence you can have higher piezo response. This gives you the advantage that we know that when you apply a mechanical stress, piezo means pressure, then if you have pressure or mechanical stress, then these materials generate an electric charge. Now, you can also polarize them at smaller electric fields. So, as we had seen that nanomaterials also have high mechanical stress capacity, absorbing capacity. That means you can apply high mechanical stress on them. So, if you can apply high mechanical stress, you will have a higher electric charge generation. Hence, you will find that you will be able to generate electricity by applying pressure or mechanical stresses in these systems, and you can apply significantly large mechanical stress without inducing mechanical failure, meaning you can have higher currents coming out of it, and then all the advantages of nanomaterials come into picture. So, if you compare what we have discussed, for example, you can use bismuth telluride in thermoelectric generators, systems like zinc oxides in piezoelectric generators, or you can have PVDF, black phosphorus, barium titanate, lead zirconium titanate, potassium sodium niobate, aluminum nitride quartz for piezo generator. So, you have these systems which can be easily used. Now, for example, if you look into PZT, this is what? This means it has lead, it has zirconium 1 minus X, titanium X, O3. So, this is the molecular formula. So, as you go on changing the value of X, let us say X can be 0 to 1. So, what you can see, as you change the value of X, you will get a new lattice stabilizing. We have seen why the doping affects the lattice parameters. As a new lattice stabilizes, the lattice parameters change. As lattice parameters change, we had seen the band diagrams change, associated Brillouin zone changes. As those changes, then the acoustic and optic modes change, and therefore, the conductivity gets modulated. So, now you can make n number of combinations by just changing X. You can get a phase diagram just like we had obtained for LSMO, and you will see that these systems have different crystal structures in different ranges, compositional ranges, and their response characteristics are different. Hence, now you will also see that they have a strong temperature dependence. They are also ferroelectric. So, all these added functionality and response parameters give you the capacity to actually choose a given composition for a given device which is required for some application by a user. So, you can have this capacity of tuning the devices as per the requirement of the end user. So, it is not that you make one device and everybody has to use that device, and making these materials are no more a difficult scenario. You can easily make these solid solution, that means single phase materials, and lot of work has been done in India and other parts of the world to make such materials in large scale. Similarly, you have various materials for utilization in thermoelectric generators. Hence, what you can clearly see that making a device is a very simple process, and you can also pinpoint the composition of a given solid solution, or you can pinpoint the material which would give the desired output, knowing that these materials also have strong size dependence, confinement effects, which modulates their conductivity as well as band diagram. You can also then easily make a choice of a material. So, clearly everything which we have studied till now can be used in these materials easily, and you are an independent entrepreneur if you develop the capacity to make these materials, because rest everything is coming in and putting these materials in a given configuration. That is why industries which are actually producing nanomaterials have become critical for any nation's development. So, we talked about some of the energy generation devices where nanomaterials are used. Let us talk about the requirement for energy storage. We will have dedicated lectures on batteries and supercapacitors later in this week, but let us understand what is a typical ion based secondary battery. Secondary batteries are those batteries which can be recharged and used for a large number of times, unlike primary batteries which can be charged only once, and following their discharge they have to be discarded or they have to be recycled and refabrication has to be undertaken so that the materials can be utilized again in a primary battery. So, when we talk about, let us say, lithium ion battery, sodium ion battery, aluminum ion battery, then we are talking about batteries which are primary batteries or secondary batteries. Yes, you gave the right answer, they are secondary batteries, because you know that you can recharge these batteries and use them for a large number of times. For example, the typical cycle life for the lithium ion batteries which you are using in your mobile phones or laptops lie between 800 to 1500 cycles nowadays. So, you can recharge these batteries so many times and then only they show significant degradation in performance, that they have to be either taken for second life application or they have to be sent for recycling. So, such kind of secondary batteries are electrochemical devices that convert chemical energy into electrical energy using redox reactions. So, you have some kind of a chemical reaction taking place, such as reduction or oxidation, and that is why you have redox reactions taking place. So, if you have reduction, you actually at that point you are taking in electrons, and if you have oxidation processes, you are becoming more positive, you are giving away the electrons. Now, you will see that a typical battery is a non-trivial device. It is not a very simple, straightforward device that you can take two materials and fabricate. It actually has much more complicated structure than what we generally believe. It has current collectors, that is substrate on which anodes are deposited. Then you have an electrolyte which facilitates the ion motion. You have a separator which is an ion conducting separator which separates the two electrodes, namely anode and cathode, from short circuiting, that is electrical short circuiting, but they allow the ion motion. So, ions can pass through, but electrons cannot. So, these batteries have a non-trivial architecture. If you look into these batteries, then during charging, ions come out of the cathode, cross through the separator and get intercalated inside the anode. That is charge storage. So, if this has to happen, you can see that the anodes have to have layered structure, so that there is a gap in between the two layers where the ions can actually move in. So, if you say a solvated ion, that is an ion surrounded by water molecules in an aqueous electrolyte system, it has to cross through a separator. Now, if I say that I use a separator which is solid, it does not allow any charges to go through, it is solid, then this battery will stop to function. But we have seen that we have structures where you can simulate channel like structures in the last lecture of the previous week. So, you can have structures which have channels or porous structures which allow the ions to go through, but they are only going to allow the ions and not the electrons. So, these are called as ion conducting membranes, similar to membranes which are there in our body. Our body has lot of ion selective membranes. So, now during charging the ions go and get intercalated, and during discharging they deintercalate, go back to the structure, and the electrons which are released, they go out from the external load, because they cannot cross through the battery, and that gives you, if you have a load, then you get the electricity flowing. So, that is a typical structure which we will discuss more in the next lecture or so. Now, you have to have the capacity of tuning these layered structures. That is what the methodologies which we have discussed for the synthesis of nanomaterials gives you the capacity. So, you have lot of use of nano size materials as anode in batteries. Similarly, you should have materials which have high surface area to allow the redox reactions. So, you have both cathode and anodes which are nano sized and they facilitate redox reactions. Hence, present day batteries are extensively dependent on nanomaterials. Similarly, you have supercapacitors which use nanomaterials. Why? A supercapacitor is an energy storage device that stores charge electrostatically and has much higher power densities than batteries, less than conventional capacitors, but they have higher energy densities than conventional capacitors, but lower energy densities than batteries. So, they bridge the gap between the conventional capacitors and batteries which were being used for energy storage. So, if you plot specific power or power density versus energy density, then you will find that batteries have very high energy densities, but low power densities. Conventional capacitors have very high power densities, but low energy densities. Supercapacitors bridge this gap, that they have higher energy densities than the conventional capacitors and they have high power densities than the batteries. So, this is where they are used. But the word supercapacitor comes that you have the capacitance values which are much larger than the conventional capacitors. So, if you look into the conventional capacitors, C is given as K epsilon naught A by D, where A is the area of the parallel plates, D is the distance between the two, K is the dielectric constant of the dielectric used in between, and this is the epsilon naught, the permittivity of free space. Now, if you want to increase this, then what is the way forward? Either you increase A tremendously. So, if you want to go from typical values of conventional capacitors, let us say 1 millifarads, you want to go to 1 farad. Then what you need to do? You have to increase the value of A by approximately 1000 times. So, you have to have a very large capacitor, or you decrease the capacitor, this value of D, that you bring them very near. If you bring them very near, there will be an electrical short circuit, and that is where the use of nanomaterials came into picture. Why? Because they have high surface area. So, they can have, let us say, 500 meter square per gram of surface area. So, your area becomes much larger. This is the specific surface area which is usable for charge storage around it. So, you can have the charge storage at each of these points. and hence you get a strategy of increasing area. You can decrease D and bring these two parallel plates near to each other by again using a permeable separator, which does not allow the electrons to go through, but allows the ions to go through. So, then you have ion separations passing through this separator using an electrolyte, and they form a charged layer which is very near to the porous electrodes, that is in the range of 1 nanometer to 10 nanometer, and hence you have also reduced the value of D. So, you can have very high area while you can reduce the value of D, and so you can easily go from 1 millifarad to 1 farads. And the specific capacitances which are being routinely reported in supercapacitors nowadays are in the range of 500 to 1000 farads per gram of the active material. So, you can bring orders of change in the capacitance. Therefore, you can, let us say you still want only 1 millifarads, then you can use much smaller quantities of the material. You can have much smaller size devices and still maintain the same value, and that is what was the requirement when we started this discussion: reduced weight, reduced size, reduced cost, and that is why such devices are being extensively used. So, you have various types of materials which are used for batteries, you have various types of batteries, you have various types of supercapacitors, and you have various types of materials. So, again you get a capacity to make a storage device as per the specific requirement of the end user. Then comes energy transmission. So, if you use nanomaterials to make the superconducting wires, then you will have nearly 0 electrical resistances in them, and we know that you can have these materials which have high surface area, you can control their grain boundaries, and they have very clear response to magnetic fields, and therefore, the quantum effects which drive such magnetic field induced responses make them ideal for superconducting applications. And that is why nanostructured superconducting materials are being routinely synthesized now, and they have become very important for power cables, magnets, or even flywheels which do not show appreciable losses. You can use the same concept now to make insulating materials. So, now you do what? You actually start using insulating material, change their band gaps, have very clear control over the structure, and then introduce the energy band structure which gives you the band gap which makes such structures in the bracket of insulating materials. Then you can have such materials which would be lighter, cost effective, while giving you the capacity to sustain higher voltages. They are stable materials, hence they will also give you the advantage of longer lifespan. So, again you can make large number of materials which can be used for different applications. So, now clearly nano sized materials and the industries which are there that are fabricating these materials have become so important, because the kind of applications which we are seeing for these materials are enormous and they are growing on daily basis. You can also use them for solar cells, you can use them for the hole transport layer or the electron transport layer, and you can also tune the semiconducting material itself such that the interfacial effects can be controlled, and when there is a light incident on it, you can control the flow of charges. I will discuss more about the solar cells in subsequent lectures, but for the time being you can clearly see that you have these materials which we have been talking about, and they have given you very interesting phenomena and response characteristics when you modulate their particle size, and therefore, you are getting high efficiency solar cells which are being reported on daily basis. You can use the phenomena of catalysis in fuel cells, where you use the catalyst to actually improve the reaction activity and stability at the electrodes and leading to the charge separation or carrying of charge, and hence giving you the storage as well as transmission capacities. So, you can again have large number of materials which can be used for various applications, and some of them are listed here. So, hopefully, now it is clear to you that nanomaterials which have the intrinsic advantage of high surface area with large number of active sites available near the surface to undergo or take part in interfacial reactions are going to become extremely important for next generation energy devices, and we have discussed from generation, storage, transmission and combined requirement of storage and generation technologies in today's lecture. You can go through some of these literature to have even more understanding about these topics, and I thank you for attending the first lecture of week 10. Thank you very much.